Data. Lesson 6.8, Simulations. So a simulation is a program that basically we use to imitate something in the real world. So for instance, like you wouldn't want to have a hurricane hit something before you understand how it works. Okay, so what you do is you usually take past data, testing data, and you try to predict what's going to happen. You make models based on these simulations. So usually you try to use real data. Okay, so you usually try to pull some past information and you put constraints on that. You want to make sure you try to reduce, you can't have too many. The more variables you have in the simulation, the more complex it gets. So you have to think about, what variables are you trying to look at? What variables can you maybe remove from the simulation? And again, the goal is to do it in a safe environment where you can run different simulations, like what if this changed? What if this changed? What if this changed? Without actually running any risks. So you can test a theory with no risk. You can determine how changes in the data can affect the outcomes. You can analyze, well, what happens with random events? Like, what if we throw this outlier in here? How would it handle it? If you have data that has a lot of outliers. So an outlier is a data point that kind of sits away from all the other ones. Okay, so maybe you have test grades, right? You've got all these students and they did really well, right? They made 80s and 90s. Then you got this one student who came in and made a 20. That one student throws down your average. But it's, that's an outlier. Like that's like, most of the people did really well. This one student was kind of an issue. So, you can kind of test those outliers. Like, how did the outlier affect your data? What if we remove it? Like, how would the data look then? Basically, it's going to answer the what if questions. So, how could severe climate affect the weather rate of a landform? You can run a simulation on that. How can an introduction of a new species affect a current species in an ecosystem? How could changes in the atmosphere affect the climate? Those are all things that you could test in a computer simulation without having, the weathering rate of a landform takes forever. Well, in a computer system, we can speed that up. Okay. So when you set up a simulation, you have to determine the goal. Like, what are you trying to simulate? What kind of outcomes are you looking for? Again, you're going to need testing data. You're going to need some kind of data to start your model with. You need to know what kind of numbers are common. Where do we start? We got to start with something. So usually you have an initial data set. So you will have to use like data collection method for that. Then you're going to create your model based on variables that you consider significant. Less variables means the model's more simplistic. More variables means you're going to have more accuracy, but your model's going to be a lot more complex. There's no set rule for that. It's one of those things where you as the developer of the model have to determine, and a lot of statistics goes into this, what variables seem to be correlated. What variables should seem to have more impact than others? Make sure we're measuring those. So it's not just plugging in numbers and then running a data simulation. We have a lot of building to do when we do it. Once you set up the model, you have to validate it. So you're going to run some tests on it and to see when you run it, is crazy stuff happening? Or is it running as expected? If you're getting odd things happening, you need to go back to your model. You need to reinvestigate it. You need to get your model good because your simulation's only as good as its model. Once you're happy with your model, then you're going to perform the simulation. Generally, you do multiple trials. You collect the data. And then at this point, you're going to analyze the results. So you'll probably make some data visualizations, run some statistics, determine if improvements could be made. When you've kind of finalized it, you're going to create documentation. You're going to write up what you found, how you set up your model, what processes you used. That way other people might want to use this. Okay, so here's a simulation of a dice game. Okay, so I don't actually have two players rolling a dice. This is just an example of if they were playing this game, this is how it would look. So each player rolls a single dice. Scores are measured by the difference in the dice. So notice in the first roll, player 1 got a 5, player 2 got a dice roll. Player 1's score was higher, And the difference between the rolls was 3, so player 1 got 3 points. On the second roll, they tied. The difference is 0. The scores did not increase. Like player 1 still has a 3, player 2 still has a 0. On roll 3, player 2 had the highest number. The difference was 3, so now player 2 gets 3 points. Okay, so you've got to look at the data. You've got to look at the number of trials and try to figure out what's the pattern. What is going on? You have to understand how this data is being built if you have any hopes of coding it. Okay, so this is just like initial data. This is telling us what's going on, and this is going to help us identify the patterns and the rules. Now, what if we wanted to simulate the score between the two players after 20 rolls? So now is where the code comes in. Okay, so first of all, we want to create a random function that generates a number between 1 and 6. Okay, a dice has numbers 1 through 6 on it. We need to simulate that. So honestly, just this random number right here simulates a dice roll. We're going to do this 20 times, so I'm going to have an integer rolls 20 times. That could be changed. Like, what if you wanted to simulate it 50 times? You would just go here and change that to 50. So that just tells us how many rolls we want to simulate. Initially, player 1 and player 2 have scores of 0, right? Before they play, they're both at 0. Okay, so for I equals 0, I less than rolls, I plus 1. So we're going to do this 20 times. Player 1 is going to roll, and player 2 is going to roll. So they're each going to roll a random number between 1 and 6. So that is a simulation of a dice roll. They're not physically rolling the dice here. The computer is going to simulate that. And remember, this is a pseudo-random generator, not a truly random generator, but for our purposes, it's good enough. Then we're going to take the difference between the rolls. So we're going to take the absolute value, because we don't want negative difference. We're going to take the absolute value of the difference of the rolls. Okay, so like 5 minus 2 or 1 minus 4, they would both give me a difference of 3. If player 1 had the higher roll, take player 1's score, take his old score, because you don't want to lose his old score, right? You're augmenting to it, you're adding to it. So take player 1's old score and add the difference to player 1. Player 1 gets those points. Otherwise, player 2 is going to get the points. Now notice if they're equal, player 2 is going to get the points, but the difference is 0, so that doesn't matter. So this code is perfectly fine. If you don't like that, you could do an else if statement where, like, if they're equal, don't change the scores. But this is fine. The roll difference, if they're equal, is 0. Adding it to player 2 is not going to affect player 2's score. Right? So now we could run this as much as we want, and we could see in the long run, does one player seem to, do they seem to get the same amount? And you wouldn't want to just do this once. When you have a model, when you do a simulation, you're going to do this multiple times to figure out, okay, well, player 1 on average is going to get what kind of score? Player 2 on average. Is player 1 typically going to win? Like, it shouldn't happen that way, but now we can test it to see. Okay, so here in video games, a lot of times the way video games work is they work on probability. When you defeat a monster and they drop an item, they have a % chance to drop certain items. So let's say in a certain video game, a player, so this is like the initial data, okay? The player goes in, defeats 25 dragons. He gets 7 tooth, 10 wing, 6 scale, and 2 heart. Those are his item drops. This is the initial data that we're going to use to create a simulation. So now the kid is like, oh, okay, or the player, I shouldn't say kid, right? The player says, okay, well, what could I expect to happen if I defeated 100 dragons or 1,000 dragons? Okay, so he's going to use his probability information to write code to simulate that. So go ahead, pause the video, see if you can come up with some code for the simulation, and then come back when you're ready to view the answer. So, first, you have some initialization due. Dragons, I use dragons, or you could do N, okay, whatever you want to call it. This is the total number of dragons he intends to kill. And then we have each item drop. Tooth, wing, scale, and heart needs to be set at 0 because when he first starts out, he doesn't have any of them. Okay, so you need to initialize your information there. Then you're going to loop through 100 dragons. So n equals a random number between 0 and 25. Why did I do this? Well, I did this because in his initial data, he defeated 25 dragons. So we need to mimic that. Like, basically, this is to get a tooth, that's a 7 out of 25 chance there. To get a wing, it's a 10 out of 25 chance. So we need that to kind of build our probabilities or our frequencies up. So this 25 came from his initial data set. It was the size of the initial set of data. If n is less than or equal to 7, we're going to give him a tooth. So we're going to add 1. We're going to increment tooth by 1. We're going to say, oh, you just got a tooth. So you got 1 tooth. Else, okay, so if n is less than 7, we're going to get a tooth. If n is between 7 and 10, we're going to get a wing. Now, you could do that using a compound inequality. Like if n is greater than 7 and n is less than or equal to 10. But it's not really giving us the right probabilities here. So what we have to do is use what we call an accumulative frequency, a cumulative frequency. So there is if n is 7, we can get a tooth. For a wing, we want to continue on. We want to add 10 to that previous value of 7. So basically, we need to make sure we're going from 7 to 17, not 7 to 10. 7 to 10 would only give us a probability of 3 out of 25. We want to make sure we're using a probability of 10 out of 25. So you want to make sure you're adding 10 to the previous value. All right, and I don't need a compound inequality because if n is less than 7, it'll do the first part and quit. So if it's bigger than 7, it'll go to this. We'll add 10, so 17 is my cutoff here. So keeping in that fashion, okay, and that's for wings, right? Keeping in that fashion, the next else if, we would need to add 6. So 17 plus 6 is 23. We need to make sure that the distance is 6 because we need to have a probability of 6 out of 25. It needs to represent that. So if n is less than or equal to 23, we would add 1 to scale. Otherwise, he's going to get a heart. Right? And this is actually very common code for how item drop rates are in video games. Now, what I showed you earlier, that was using frequencies. I think that might be a little bit more straightforward with the numbers we were given. But you could actually redo it using probabilities. So if you do 7 divided by 25, you get 0.28. 10 divided by 25 is 0.40. 6 divided by 25 is 0.24, and 2 divided by 25 is 0.08. If you choose to use the probability instead of the frequency, your random would not, you wouldn't want to choose a random number up to 25. You would just want to choose a random decimal value between 0 and 1. Okay, so that would be a little bit different. Instead of using the frequencies here, you would have 0.28 as your cutoff for the first one. Then you would add 0.4 to that. So you still have to accumulate it. You still have to do a cumulative probability. You're just using the probability values instead of the frequency values. So if we add 0.4 to that, we get 0.68. If we add 0.24 to that, we get 0.92 for scale. And then else, the else statement is still heart equals heart plus 1. Okay, so these are equivalent as far as what they do. It's just this one uses frequencies, this one uses probabilities. If you're teaching this, unless your students have done probabilities in the past, frequency might be the better choice. Okay, and as always at the end of the unit, there are some resources on the slides that you can go to learn more about some of the topics covered.